All right. In this video, we will be starting chapter 5. Basically, in chapter 5, we will be discussing various techniques to integrate different types of functions. Okay. So we are going to start with section 5.1. The first technique that we are going to learn in integrating functions, which is called the substitution, integration by substitution. Okay. 5.1, integration by substitution. I want to start with this theorem, a formula for integration by substitution. Okay, here is what the theorem tells us. If f and u are functions such that f prime of u of x times u prime of x is integrable, then the integration of this particular function, f prime of u of x plus u prime of x, is equal to f of u of x plus c. Okay, you should be familiar with this one with previous sections. This is actually, if you carefully look at this one, this is the derivative of this function, right? This expression is the derivative of this function, or in other words, this is an antiderivative of this function. If this is an antiderivative of this function, then the integral, the indefinite integral of that function should be that antiderivative plus a constant c. Okay, it's a kind of a straightforward rule. You can undo the chain rule with a method known as integration by substitution. That method is also called U substitution, and that's what we will be discussing in this section. Okay, the key to U substitution is the change of variable. We use a change of variable when we apply U substitution. Okay, we will be seeing in the examples that we will be discussing. First of all, let's see how to undo the chain rule for a particular example. I'm going to take f of x to be sine x, u of x to be x squared, and then clearly f prime of x is cosine x, and u prime of x is 2x. That's clear. Okay. Now, if you try to apply this rule here, I can find the integration of this particular function. Notice that this is f prime of u of x. This is exactly this term, because my f prime of x is this expression cosine x. Then f prime of u of x would be, you replace here this x by u of x, this x by u of x. Your u of x is x squared, that is cosine x squared. This is actually f prime of u of x, and this is precisely u prime of x. U prime of x, the derivative of this function. Okay, so that means we have this exact form over here. So this is f prime of u of x times u prime of x. So the integration should be f of u of x plus c. F of u of x. What is f of u of x? To find f of u of x, you need to replace this x by u of x. This x by u of x, you get sine x squared plus the constant. Okay. So this is a straightforward example, but in this example, we already took these functions. So our life was easier. It was just a comparison between this expression and this expression, and we can straight away apply this rule. But what if you are directly given this function, this integration, without giving any of this information? Can you still handle that? That's where the U substitution is going to help you. Okay, we'll be discussing how to apply U substitution to integrate functions like this. Basically, integrate products, because so far we don't have any existing method to integrate this kind of a product, right? We have not discussed. So to integrate these kind of products, we can use this technique of U substitution. All right, before we go to the U substitution technique, I want to discuss a few more things. Let's look at this particular integral. What is the integration of f prime of u du? The indefinite integral of f prime of u du, that is clearly f of u plus c, right? Because we know that f of u is an antiderivative of f prime of u, because if you differentiate f of u, you get exactly this expression, f prime of u. So that means the indefinite integral of f prime of u du is equal to f of u plus a constant. So we have that. So what about if this u is a function of x now? If u is equal to u of x, then this integral becomes that integral becomes integration F prime of U of X. I'm plugging U of X in place of U, and then here you have D of U. Well, it is D of U of X, but I will keep U there because U of X is same as U, so I'm going to keep U there. And then that is going to be equal to, on the other side also, I'm going to plug in U of X in place of U plus a constant. Now, as you can see, if you compare these two equations, this is the undoing of the chain rule, okay, that you saw in the previous theorem. If you compare these two formulas, the right-hand sides are same. This is same as this one. Not only that, even in the left-hand side, this first term is the same, F prime of U of X. So this suggests that these two have to be equal, du and U prime of X dx. Okay, because your right-hand sides are equal. These two sides are equal. That means your left-hand sides must be equal. On the left-hand side, these two expressions are already equal. So it suggests that du must be equal to U prime of X times d of X. Okay, that motivates our next definition. Okay, let's define du there. Basically, du is equal to U prime of X times dx. Here is the definition that we have. The differential of a function. If U of X is a differentiable function of X, then differential du is equal to, here is how you define it, du is equal to U prime of X times dx. That's what exactly I suggested in the previous case. Du has to be equal to U prime of X times dx. That's what I am claiming here. All right, now we are ready to use U substitution technique. Okay, let's see how we can use the U substitution technique. Here is the same example that we took in the previous case. This is the example that we wanted to focus on, right? So let's think about that example using the doing that example using U substitution. Okay, so here what I'm going to do is I'm going to take, as you can see, if I take this to be my U of X, I have the derivative of that outside, right? That's the key to U substitution. If you take U to be a certain function, inside function, then the derivative has to stay outside. That's the key to U substitution. I will take U is equal to X squared in this case. Then clearly du over dx is equal to 2x. Now, the previous theorem, previous definition suggests that du is equal to U prime of X times dx. So that means du is equal to, of course, U prime of X is this one. This is the derivative of U. U prime of X times d of X, that is 2x times dx. I know that du is equal to 2x times dx. Now I can write this integration purely in terms of an integration of U. That's what I'm going to do. Okay. Now my original integral is equal to, that is this integration, cosine x squared dx okay, this original, pardon me, we should have 2x here in addition. X is dx, of course, is equal to integration cosine. Now I'm using my U substitution. Remember, x squared is U. So let me put U here. X squared is my U. You should have U here. Times, here we have 2x times dx. But I know that 2x times dx is exactly du. I can put du here. If I put du here, this is what you get. Now, as you can see, this is a familiar integral to you. You know how to integrate this particular function, cosine u. You know how to integrate cosine u. The integration of cosine u would be sine u. Plus c. Of course, you should have a constant. But remember, you are not done yet, because your original integration was in terms of x. So you need to leave your final answer in terms of x. All what you need to do is you replace this u by x squared, because you know that u is equal to x squared. That's the substitution that we used. So this is equal to sine x squared plus c. And of course, you can verify that this answer is correct by differentiating this function. This should be an antiderivative of this function, right? See whether if you differentiate this one, you get this particular function. Of course, if you differentiate this one, the derivative of sine is a cosine x squared. Of course, you have to use the chain rule that will give you this function. So we are on the right track. So this is how the U substitution works. Okay, this is a very simple example, and in this section we will be applying this U substitution technique to various integrals, basically to products. All right, let's move on. Okay, the next example that I want to work on is this particular example. Use integration by substitution to find this particular integral. Okay, sometimes you say integration by substitution, sometimes you say by U substitution. Okay, those are synonyms. All right, let's try to use the U substitution here. So how can we use U substitution here? What should I take as U in this case? Well, there some sort of intuition is needed to guess which function you are going to take as U of x or U. Okay, in this case, I will take my U as this function. If I take this as U, then the derivative of this function is 35 times x to the power 6, right? X to the power 6 is sitting here. That means the derivative of this function is a constant multiple of x to the power 6. That's what exactly I want. Remember, when you use the U substitution, your derivative of that U should be sitting there right next to the this function, right next to this function. Okay, looks like the derivative part is already there, but not the exact derivative, but the derivative of this one would be a constant multiple of x to the power 6. That's okay. All right, so I'm going to take U to be 5x to the power 7 minus 2. That will immediately give me du over dx is equal to 35x to the power 6 okay, this will give me du is equal to 35x to the power 6 dx. You just send this dx to the other side. Okay, or you are simply applying this definition. Du is equal to always u prime of x times dx. Okay, you can think of that as sending this dx to the other side. That will give me this equation. But this is not quite what I want here. I want here I have x to the power 6 times dx, right? I don't see a 35. In this expression, in this integration, I don't see a 35. So what I'm going to do is, before I do anything else, I'm going to divide 35, both sides by 35. Then you get 1 over 35 times du is equal to x to the power 6 times dx. Now, as you can see, you can find exactly this expression in the integration, x to the power 6 times dx. Okay, I can reply that product by this expression. Okay, all right, that's what I'm going to do. Now, let's go with the U substitution. I'm ready to start the U substitution process. Here, I have, notice that I have here x to the power 6 times dx. I'm going to replace that by 1 over 35 times du. And of course, this is my u. I'm going to put u here. That will give me e to the power u times 1 over 35 times du. I'm replacing x to the power 6 times dx by 1 over 35 times du. So this is what you get. And of course, now you can pull out your 1 over 35, which is a constant. You get e to the power u du. This is an integration that you're familiar with. You can integrate this using the basic rules that you have learned so far. Okay, the integration of e to the power u with respect to u. Okay, definite integral of e to the u du is equal to, of course, I need to have this constant in front. That is going to be e to the power u itself plus c. Okay. Now this is equal to 1 over 35 e to the power u plus, notice that here I'm multiplying 1 over 35 by c. C is a constant. Then you again get a constant, right? So you don't really have to write 1 over 35 times c. You can just put another constant there. C prime or something. Okay, it's another constant. All right, so your integration will become, of course, I can go ahead and plug in the value of u, 1 over 35 times e to the power, your u of x is 5 times x to the power 7 minus 2. 5 times x to the power 7 minus 2 plus c prime. So this is the integration. Of course, you can check whether this is correct or wrong by differentiating this antiderivative, by differentiating this expression. If you, when you differentiate this expression, if you obtain this integral right here, this function right here, then your integral is correct. Okay. All right. Okay. In the U substitution process, I will write my original integral here. Okay. Original integral is equal to, here is the integral that you obtain when you use the U substitution. Okay. It boils down to this integration, and of course you can integrate this and you can back substitute for u to get your final answer. All right, so that completes that example. Let's move on. All right, let's next we are going to work on this example. We have several parts. We need to determine whether a U substitution would be appropriate in this case or not. Okay, let's address one by one. If you take the first part, would a U substitution be good in this case? Well, to determine that, if you take your inside function to be u of x, its derivative should be sitting right next to that. It can be a constant multiple though. Okay, if you have the derivative of the function that you are going to take as u of x in the side of the function, this function, then we can apply the U substitution. Okay, in this case, if you take u of x to be this function, as you can see, the derivative of that function u of x would be a constant multiple of this function. So we are good to go with the U substitution. Okay, so in the U substitution case, I'm going to take u is equal to x to the power of 5 plus 1. Then immediately this will give me du over dx is equal to 5 times x to the power 4. That will give me du is equal to 5x to the power 4 times dx. Notice that I want here x to the power 4 times dx. I don't need a 5. So I'm going to divide both sides by 5. That will give me 1 over 5 times du is equal to x to the power 4 times dx. Now I am all set to go with the U substitution. Okay, now let's use the U substitution here. So my original integral, which was integral x to the power 4 square root of x to the power 5 plus 1 dx is equal to, if I use the U substitution, notice that x to the power 4 times dx is 1 over 5 times ux. I can replace that by 1 over 5 times du, and of course this is your u. So that will become square root of u times 1 over 5 times du. This is, if you pull out 1 over 5, indefinite integral of square root of u du. Now you know how to integrate this function. Okay, this is a very simple function. You know how to integrate a function like square root of u with respect to u. Okay, and then you can integrate this one and back substitute for u. Remember, your u is x to the power 5 plus 1. Okay, for the first example, I will show you the final answer, but for the next part, I will bring you to a place where you can integrate, and then I will leave it for you to integrate it. Okay, this will be 1 over 5 times the integral of square root of u would be u to the power 3/2 divided by 3/2 plus the constant c. This will be 1/5 times, of course, your u is x to the power 5 plus 1 to the power 3/2 divided by 3/2 plus c. That's your answer. Okay. And of course, you can verify that this answer is correct by differentiating this part and showing that that's an antiderivative of this original function. Okay, you can see that if you differentiate this function, you will get this function. All right, let's move on to the next part. Next part is part B. Okay, if you look at part B, if you take this function to be u of x, the derivative of that function would be 5 times x to the power 4. It doesn't give x to the power 3. So that means in this case, the derivative is not sitting by the side. Okay, so even if you take this to be u of x, again, you will see that this is not going to be the derivative of that one. So in this case, we cannot use the u substitution. U substitution would not be the best way to do this problem. Okay. U substitution would not work. Okay, let's move on to part C. Okay, in part C, clearly u substitution will work. If you take, this is the square function, inside that you have sine x. If you take u is equal to sine x, the derivative of sine x is cosine x. That is sitting right next to that expression. Okay, so in this case, u substitution will work. You may use u is equal to sine x. If you use u is equal to sine x, du over dx is equal to cosine x. That will immediately give us du is equal to cosine x dx. Now I can start with the u substitution process. So that will give me cosine x sine squared x dx is equal to, I'm going to go with the u substitution. Notice that cosine x times dx is nothing but du. I can replace that by du. Of course, this one is just u squared because I'm taking u to be sine x. U squared du. Notice that again, cosine x dx. That is equal to du. Okay, so I put du here. This is an integration that you know. Okay, you know how to integrate a function like this u squared. Okay, that's u to the power 3/3 plus a constant. Okay, so you can go from there. I'm not going to get the final answer for these integrals. Okay, because you are familiar with these things. Please go ahead and find the integration of this one and make sure that you back substitute your u to get the answer in terms of x, not in terms of u. All right, let's move on to part D. Again, in part D, a u substitution will work. Okay, if I take u to be 1 plus e to the power x, that will give me du over dx is equal to e to the power x. Of course, that means du is equal to e to the power x times dx. Notice that in this integral, you have e to the power x times dx. That is exactly this one. I can replace that by du. And of course, your bottom is u. I took this to be u. Okay. Now I can go with the u substitution process. That is integration e to the power x over 1 plus e to the power x dx is equal to integration. Remember, e to the power x times dx is nothing but u du. Pardon me, du. Okay, and then you have 1 over u du, because this is your u. So you have 1 over u, and this expression is du. So you have 1 over u times du. Again, this is an integration that you are familiar with. Okay, you know how to integrate functions of this form, so you can integrate that. Okay, make sure that you obtain the final answer and make sure that you back substitute for u to get the answer in terms of x. All right, what about part E? Oh, actually we did part E. Okay, good. We missed something. That means this is part E actually. And then let's do part D. We missed part D. What about part D? Again, clearly in part D, the derivative of tan x is not equal to, if you take this to be u, the derivative of that is not equal to the remaining function. And on the other hand, the derivative of this also is not equal to tan x. So the u substitution is not going to work here. Okay, but using some algebra, you can easily integrate this one, because if you think about this tan x is sin x divided by cosine x. This is actually sin x divided by cosine x, and then this cosine x and this cosine x will be cancelled. Actually, you have integration sin x dx, and you know how to integrate that. Okay, but the u substitution will not work here. U substitution will not work. Okay, next we go to the last part. In the last part also, you will see that u substitution will not work for this example. For example, you can take this to be u of x and see whether you can go with the u substitution. You will see that a u substitution is not going to work anymore here. And even if you take u of x to be this function e of x, again you will see that u substitution will not take you any longer anywhere. So u substitution will not work here. I'm not going to give the detail for this one, because detail are similar to previous example that we discussed. U substitution will not work. All right, let's move on. Next, I want to work on this example. Use integration by substitution to find this particular indefinite integral. Okay, so here is the substitution I'm going to use in this case. This is an interesting example. As you can see, if I take this to be u of x, the derivative of that is not right beside of this side, right beside this function, because the derivative of x minus 1 is just 1, right? But still you can use the u substitution in this case. That's why this example is interesting. Okay, even if you don't have the derivative, if you have the derivative of your u of x right besides that function, that's great. Okay, that's the ideal environment for you to apply u substitution. But here is an example where you can still apply u substitution even if you don't have the exact derivative. Okay, so now let's see what happens if you use the u substitution here. I'm going to use u is equal to x minus 1. Then clearly du over dx is equal to 1. That means du is equal to dx. Notice that when you write this way, I can isolate my x. X is u plus 1. My x is u plus 1. Wherever I see x, I can replace that by u plus 1. Now I'm ready to start the u substitution process. Integration x square root of x minus 1 dx is equal to integration. Remember, my x is nothing but u plus 1. I can replace this x by u plus 1. Times square root of u. Remember, x minus 1 is u. That's my substitution. Times dx. Dx is nothing but du. Du and dx are, they are equal. Okay. Now this is an integration of u. This is purely an integration of u. Of course, you can simplify this. You get u to the power 3 over 2 plus u to the power 1/2 du. Okay. All I did was, this is nothing but u to the power 1/2, and you distribute that inside, then you get u to the power 3 over 2 plus u to the power 1/2. And now you know how to integrate a function like this. You are familiar with how to integrate in a function like this. You can integrate this function using the known techniques and find the answer. Okay, let's do that. So if you integrate this part, you get u to the power 5 over 2 divided by 5 over 2 plus u to the power 3 over 2 divided by 3 over 2 plus a constant. Remember, this is not your final answer. You need to back substitute for u. Your u is nothing but x minus 1. Let's go ahead and back substitute that. All right, if I do that, you will get, I'm using the reciprocal rule to simplify this fraction, 2 over 5 times x minus 1 to the power 5 over 2 plus 2 over 3 times x minus 1 to the power 3 over 2 plus a constant. Okay, that's your final answer. All right, let's move on. All right, let's move on. Okay, let's work on this example. Again, we have to integrate these functions. Okay, so let's work on part A. How would we integrate this function using U substitution? Well, you have only two choices. You take either u is equal to ln of x or u is equal to x. Okay, u is equal to x would not take you anywhere. But if you take u is equal to ln x, that will take you to an integration where you can do by your existing formulas, okay, existing knowledge. All right, let's see how we use the u substitution. I'm going to take u is equal to ln x in this case. Then that will give me du over dx is equal to 1 over x. Okay, or in other words, my du will be equal to 1 over x times dx. But see, look at the integration. Here you have 1 over x times dx. So you can replace this 1 over x times dx by du. Okay, right there you have the integration in terms of u, because you are just putting u here, right? Because your u is equal to ln x. Let's do the u substitution process now. You have ln x. Always write the original integration first and then write the u substitution. This is equal to ln x is u times, remember, 1 over x times dx is du. This is equal to u squared over 2 plus a constant, that is nothing but u. Your u is ln of x. ln of x squared over 2 plus a constant. This is your final answer. Of course, you can verify that this is the correct integral. This is the correct answer by differentiating this one and showing that it is an antiderivative of this original function. If you differentiate this function, you should get this one. All right, let's go to the next part, part B. Part B, again, I'm going to use a u substitution. This time, I'm going to use u is equal to square root of x and see what happens. If I take u to be square root of x, that will imply du over dx would be 1 over 2 times the square root of x. Okay, you know how to take the derivative of functions like this. This is x to the power 1/2. If you take the derivative of that, you will see that that is going to be 1 over 2 times the square root of x. This will give me du is equal to 1 over 2 times the square root of x times dx. I'm just sending this dx to the other side. Okay, so you have this equation. But if you go back and investigate your original integral, here I have 1 over square root of x times dx. But I have a 2 here in addition to that 1 over square root of x times dx. Of course, I have that term here. but I have a 2 here. So what I'm going to do is I'm going to bring this 2 back to the left hand side. That means 2 du is equal to 1 over square root of x times dx. Now, as you can see, I have an expression for this one. That's what I have here. 1 over square root of x times dx. That's exactly this one. That is equal to 2 times du. I can replace this part by 2 times du. Okay. Now let's go with the U substitution process. Integration sine square root of x divided by square root of x dx is equal to integration sine u. Square root of x is u. That's what I'm taking. Times, remember, 1 over square root of x times dx is exactly 2 times du. I'm going to put 2 times du here. Now I can pull out my 2. That would be integration sine u du. That's going to be 2 times minus cosine u. We know how to integrate sine u. Sine u, the integration of sine u is minus cosine u. Should have a parenthesis here plus a constant. Okay, that's what I have. So now, are we done? Remember, we have to do one last step. You have to replace this square u by square root of x, because that's the substitution, because our initial integration was in terms of x. That's going to be minus 2 times cosine square root of x plus c. Okay, so that's the final answer. All right, let's move on. Then we have this theorem. Integrals of tangent and cotangent functions. The integration of tan x is, the indefinite integral of tan x is ln's absolute value of secant x plus c, and the integration of cotangent x is minus ln absolute value of cosecant x plus c. Okay, how do you know that these formulas are true? How do you prove that these formulas are true? All what you need to do is show that this is an antiderivative of this function tan x. How do you show that this is an antiderivative of tan x? You differentiate this function and show that you get tan x. Again, to prove this formula, you show that the derivative of this function is cotangent x. Okay, that will show that this integration equation is true. Integral equation is true, or integration formula is true. All right, let's move on. Next, we have this theorem evaluating a definite integral after a substitution. That's very important. Okay. If f of x, here is what the theorem tells you. If f of x is equal to g of u of x is continuous on a comma b closed interval, u of x is differentiable on the open interval a comma b, and uppercase g of u is an antiderivative of lowercase g of u. Then we have this definite integral formula. The definite integral from a to b f of x dx is equal to, you put the x limit here, g of u du is equal to, remember, an antiderivative of g of u is uppercase g of u. You plug in g of u here and you put the x limits. Remember, still you have x limits. Here you started with x limits, you have x limits, you have x limits, you keep the x limits. Okay, here also you have x limits. Okay, so now what you do is, here you have g of u, but I know that u is u of x. Okay, u is u of x. I'm going to replace this u by u of x. That's your substitution. Remember, usually you use u is equal to u of x. So I can replace this u by u of x. U is a function of x. Now you can plug in the x limits here to this inside input. You replace, you plug in upper and lower limits for this function. This is the evaluation notation, right? If you have a function like this, you plug in the upper limit and then minus, plug in the lower limit. You get g of u of b minus g of u of a. Okay. And next theorem tells us a way to go with u limits instead of going with x limits. Here, see, we went with x limits forever. Until we get the final answer, we stick to x limits, right? But the next theorem tells you a way to go with u limits instead of x limits. Okay, let's look at that theorem now. Okay, let's look at the next theorem. If f of x is equal to g of u of x is continuous on the interval, here there's a typo, there's no u here. Let me fix that. All right. If f of x is equal to g of u of x is continuous on the closed interval a comma b, u of x is differentiable on the open interval a comma b, and g of u is an antiderivative of lowercase g of u, then the definite integral from a to b f of x dx. Remember, these limits are for the x limits. These are the x limits. Is equal to, after you do the substitution, you come up with an integration in terms of u. For that, now what you can do is, since you know that your u is equal to u of x, u is equal to u of x, now this is an integration with respect to u. Now you can actually find the u limits. We know the relationship between u and x. Okay, when x is equal to a, you can find the u value by plugging your x value here. If you plug in x is equal to a here, you get u of a. Okay, so that means u limits would be u of a to u of b. Of course, you obtain this upper limit by plugging this limit, this x value in the function u. Okay, you get u of b. So now you have the limits for u. These are called u limits. Now you have the integration from u of a to u of b. Those are the u limits. Okay. Now, of course, since we are given that uppercase g of u is an antiderivative of lowercase g of u, the integral of this one, this function g of u, would be uppercase g of u. Now you can plug in the u limits. This time not the x limits. Now you are directly plugging u limits, u of a to u of b. This is the evaluation notation. If you plug in u is equal to u of b, you get this expression. And if you plug in u is equal to u of a, you get this expression. Notice that both answers are same. This is same thing as this in the previous theorem. Okay, that's the idea of definite integral when you use substitution. All right, let's work on this example. Again, we are going to use U substitution. Let's do this in two ways. The first way is, let's stick to x limits till the end of the calculation. And then in the next part, we will stick to u limits and do the calculation. Okay. So first of all, I need to find a substitution to do this problem. Forget about these limits. Let's try to just integrate this one without limits. Okay. So for that, what would be a suitable substitution? Well, I'm going to take u is equal to 3x squared plus 1, because if I take that way, you have the derivative here, not the derivative, but the constant multiple of the derivative, right? So you have it here. Now, if you take u to be having a constant multiple of the derivative right beside the function, suggests that u substitution would be good here. So if I take this to be my u of x, or u, du over dx would be equal to 6x. From here, I get du is equal to 6x times dx. Notice that here I have x times dx, not 6x times dx. So I'm sending this 6 to the other side. 1 over 6 du is equal to x times dx. Now I'm ready to go with my u substitution. You should have 1 to 4. Remember, when you say 1 to 4, these are the x limits. Okay, keep that in your mind. So this is equal to x dx, which is 1 over 6 times du. x dx is 1 over 6 times du. So I can put it there, and I have 1 over u times 1 over 6 times du. This is equal to, of course, I can pull out 1 over 6, integration 1 to 4. So I will write, since this is an integration in terms of u, I will write x is equal to 1 to x is equal to 4 to indicate that these are x limits, not u limits. You have 1 over u du. That's what you have. All right. We all know how to integrate this function 1 over u with respect to u. That will be 1 over 6 times ln absolute value of u. The integration of 1 over u is ln absolute value of u. Of course, I have to put the limits now. Integration limits in the evaluation notation. That will be x is equal to 1, x is equal to 4. The upper limit is x is equal to 4. The lower limit is x is equal to 1. I'm writing this letter x because this is an expression in terms of u. Okay, that's why, to distinguish that these limits are for different variables. So I'm putting x is equal to 1 to x is equal to 4. Now, what do I have to do? Now remember, I have to get this as a function of x, not as a function of u, because I have x limits here. I'm going to live with x limits till I get the final answer. So I'm going to replace this u by my substitution, 3x squared plus 1. This is equal to 1/6 ln 3x squared plus 1, of course, the absolute value of that. Now I can just write 1 to 4. I don't really have to write x is equal to 1 to x is equal to 4 because I know that that function is in terms of x. Okay, so now I can find the answer easily here by plugging numbers. 1 over 6 times, you get ln. If you plug in 4 here, you get 49, ln 49 minus ln 4. If you plug in the lower limit here, you get ln 4. I don't really have to put absolute value here because that's a positive number. I can just write ln 49 minus ln 4. Okay, that's your final answer. Okay, that's how you do using x limits. Okay, let's do the same problem this time using u limits. Okay, all right, I'm going to copy some of the work to the other page. By the way, I'm going to have x is equal to 1 to x is equal to 4 here, okay? Because that's an integral in terms of u. I'll make sure that my integration limits are for x. All right. And by the way, this whole thing is equal to this original integral, okay? Maybe I will copy that over here. Okay, it becomes this original definite integral is equal to an integral, definite integral involving u. Okay, and then rest of the procedure is same. All right. Next, let's try to do the same example using u limits. All right. Here I have copied down the previous steps here. Of course, you take still you take u to be 3x squared plus 1. That is the bottom function. And then you find that 1 over 6 times du is equal to x times dx. Now you can use the u substitution. X times dx is 1 over 6 times du, and this is 1 over u. So you have 1 over u. Now, as you can see, these are the x limits, right? Now what I'm going to do is I'm going to find the u limits and put them here. How do I find the u lower limit for u when you know that lower limit for x is 1? All what you need to do is you plug in this 1, this lower limit for x here to find the u lower limit. So that means you plug in 1 in the function u of x, u of 1 will be 4. As you can see, u of 1 will be 4. And then what is u of 4? The upper limit. To find the upper limit, when x is equal to 4, to find the u limit, you plug in 4 in your function. X is equal to 4 in this function. That will give you 49. So we have the upper limit and the lower limit for u. That's not for x. These are the lower limits and upper limits for u. Now let me put those limits here. That is 4 to 4 to 9. 49, pardon me. The definite integral from 4 to 49, 1 over u, 1 times 1 over 6 times du. Again here, 1 over 6 walks out, 4 to 49. Now, if you integrate this one, you know how to integrate this function with respect to u. So you will get 1 over 6 times ln absolute value of u. Now you can plug in this limit straight away because those are u limits. These are not x limits. These are u limits. So you can plug in those limits straight away and you will come up with the same answer. 1 over 6 times ln 49 minus ln 4. That's the final answer. And that's the same as the answer that you obtained in the previous system. Okay. That's how you do problems with x limits. And this is how you do with x limits. And here is how you do the same problem with u limits. Okay. With that, we conclude section 5.1. I'll stop there. I'll see you next time.